Hello and welcome to Lecture 3 for Math 114, 1114. Today we're going to be talking about Section 5.2, which is the definite integral. I do want to mention that I'm making an effort to make these video lectures different than the way that they're presented in the book. So it's very useful to you to also read your book, especially the ebook, and play with the interactive figures that are there. They kind of can go through it slower in a way, and having both presentations together will reinforce the concepts. All right, so we're going to be talking more about area today, as you might have guessed. What we talked about last time, if you remember, is we're trying to find an area under a curve, and we had divided it up into rectangles, and we found the area of each rectangle by finding the height and the width, and then multiplying them together to find the area, and then adding up the areas of all the rectangles, which is what the sigma notation told us. So let's remember what the right endpoint formula was for that. Remember, right endpoints are the easiest because that's where the grid, or the point you're plugging in, is the same as the grid point. You notice sometimes I write i's and sometimes I write k's. It doesn't matter. You know, it's just a variable that indicates the number of the rectangle you're on. Okay, so height of the rectangle. So this was the harder one, remember? The height was supposed to be based on the function, so it's going to be f of something. And we just get the name of the point we plug in is always x bar, and then we put a sub k because it's rectangle number k. And then in this particular case, this was f of just the grid point, x sub k, and the formula for that grid point was a plus k delta x. So f of a plus k delta x is the height for rectangle number k. The width of rectangle number k was just delta x, and that was always b minus a over n. So the area is going to be the height, f of a plus k delta x, times the width, delta x. And if we add up all the rectangles, starting at rectangle 1, ending at rectangle n, all these areas, then we get an approximation for the area under the curve. And this symbol here means approximately equal to. But now today, we don't want an approximation, we want the exact area. So how can we make this estimate, this approximation, better and better? Well, if we look back at the picture here, we talked about last time if you have more rectangles, the approximation is better and better and better. So if we go all the way up, the computer here goes as far as 200 rectangles, and even with 200 rectangles, that looks pretty close. Now, what if you wanted to be even more accurate than 200 rectangles? Maybe you'd try 1,000 rectangles, or maybe you would try 100,000, 1,000,000. But to get the exact area, what we need to do is actually take a limit. So we're going to take the limit as the number of rectangles goes to infinity of this sum. K goes from 1 to n, f of a plus k delta x times delta x. And that's the exact area. So let's try that. We have already talked about finding the area under x squared between 0 and 1. So let's see if we can find that exact area. So to do that, we're looking at the limit as n goes to infinity of the sum, k goes from 1 to n, of f of, well, a in this case is 0, that's the left endpoint, 0 plus k times, we need to figure out delta x. So how do we find delta x? It's b minus a over n. So it's 1 minus 0 over n, or 1 over n, because remember, a is always the left endpoint, so in this case it's 0. B is always the right endpoint, so in this case it's 1. So we get 1 over n as delta x. And that is the height, f of x bar. And then we also have the width, which is just delta x. Okay, now the only thing we haven't actually dealt with yet is this f right here. So this is f of a point. This is our point, which we can just call k over n. And so we need to plug k over n into our function. Our function is x squared. So everywhere you see an x, you're just going to put a k over n instead. So it's going to look like limit as n goes to infinity of the sum, k goes from 1 to n, of the quantity, something squared, times 1 over n. So instead of an x, I just put these open parentheses, and in those parentheses I put my x bar value, which is, in this case, k over n. Okay, so now we have the limit of a sum of an expression. And now you've done limits before, right? You did limits in a previous class, and you know how to take limits to infinity. But what's different about this limit than other limits you've done before? Right, it has the sigma right here. And that wouldn't matter except for the sigma actually depends on n. So you're going to be adding up different things depending on what n is. And that's not okay. So what we need to do is find a way to take this entire expression and rewrite it without the sum. Now, do we know any way to do that? Do we know any way of getting rid of sums? That's right. If we want to get rid of a sum, we can use the formula sum of 1 equals n, sum of k equals n times n plus 1 over 2, sum of k squared equals n times n plus 1 over 2, or n times n plus 1 times 2n plus 1 over 6, actually, and sum of k cubed, which is quantity n times n plus 1 over 2, the whole thing squared. So we have those formulas for getting rid of sigmas. Now remember, when you're doing this, it's always k goes from 1 to n. But we don't have just one of those problems here. We have this complicated expression, right? So what do? We also can use the sigma notation simplification rules. So if you have the sum of something plus something, you can split it up. And if you have the sum of a constant times something, you can pull the constant out. So what of those rules can we use right away? Well, we're not adding anything. Do we have any constants? Actually, we do. So our constant here is the n. So because when I say constant, the only thing that's actually changing as we add stuff up is k. So we can't pull out k's, but we can pull out the 1 over n. In fact, we can pull out the n squared on the bottom down here as well. So let's rewrite this as limit as n goes to infinity of sum, k goes from 1 to n, of 1 over n cubed times k squared. And then we can take that 1 over n cubed out front. So we get limit as n goes to infinity, 1 over n cubed, sum, k goes from 1 to n, of k squared. And now that sum is exactly one of the formulas we have. So using that formula to replace the sum, we get limit as n goes to infinity of 1 over n cubed times the quantity n times n plus 1 times 2n plus 1 all over 6. And now this really is a limit problem that you could have seen in a previous class. So how does this limit work? We're taking the limit to infinity of a rational function. And if you remember, there was a theorem you learned about that. If you didn't learn it, you're going to learn it now. It says that whenever you're taking a limit to infinity, it can be negative infinity as well, but we're only going to use infinity here, of some rational function, I don't know, then you don't have to worry about all the terms. You take the highest power of x in the top, so that's the 7th, and the highest power of x in the bottom, so that's the negative 13th x to the 7th, and you can forget everything else. So you can really just look at limit as x goes to infinity of 5x to the 7th over negative 13x to the 7th. But if you're looking at that, the x to the 7ths cancel, and you just get negative 5/13. So we're going to apply that idea back to our problem here. And we need to figure out what our highest power of n is in the top and what our highest power of n is in the bottom. Well, the bottom is pretty straightforward. If I simplify all this out, the bottom is just going to be 6n cubed. So that's apparently my highest term. Now the top, I would have to FOIL all that out. Except that I don't, because I know that the highest power is going to come from the highest power of n in each of the factors. So if I multiply all those together, I get 2n cubed. And then if I FOILed it out, there'd be other stuff. But the highest power is going to be the 2n cubed on top and the 6n cubed on the bottom. That means that using my theorem, I only have to worry about those two. And that means I can cancel my n cubes and I get 1/3 as my area. And that is the exact area under x squared from 0 to 1. Okay. So now I told you that today was about a definite integral. So what is a definite integral? Definite integral is a notation, the word for taking a Riemann sum and then taking the limit as n goes to infinity. So I want to remind you, we talked about a Riemann sum, a more general type of Riemann sum than just a right Riemann sum last time. We said that you could actually, you don't have to pick your x bar as the right endpoint. You can actually pick for each rectangle, you could pick a different pick x bar in a different way. So you could pick the right endpoint for some, the left endpoint for some, the midpoint for some of them, some just random point in the base of the rectangle for others. And that will still give you a Riemann sum. But in this case, here, as you let the number of rectangles go to infinity, these are all going to get infinitely skinny, right? The more rectangles, the skinnier they're going to be. And so it'll still go to the exact area. And this, remember, we called this just a plain Riemann sum. Now today we're going to talk about a general Riemann sum. So this is even more general. So not only can you pick your x bars however you want, you can also have a different delta x for each rectangle. All right, so this is really, you got all the freedom in the world. Now the one downside of this is that if you just let the number of rectangles go to infinity, that's not going to be good enough, because you could have an infinite number of rectangles in here and still have one big wide one in the middle. So instead of saying that the number of rectangles is going to go to infinity, for this one we're going to say that the size of all the delta x's is going to go to 0. So for every delta x, the book just says delta. All the changes are going to have to go to 0. And then we're still having the sum from 1 to n, f of x bar k times delta x. Now the delta x also needs a k now because it's a different number for each rectangle. And this is the most general, without the limit, that's the most general Riemann sum. This is the Riemann sum. And then once you put the limit on, that makes it a definite integral. So this whole thing with the limit is a definite integral. And that's a lot to write, so we have a different notation for it. This is the integral notation. This sign is an elongated S. This is an integral sign. So it's a stretched out S, and it also stands for sum, just the same way the sigma does. So those match up. And then we have the going from A to B. That means just the area under the curve between A and B. And that's matching up with the limits from 1 to n in your sum. And we also have our function, the same way we have it over here, telling you what function you're using. And then the last part is dx, which compares with the delta x. So the dx is infinitely small delta x. Okay? So this is how we define the definite integral. The reason we have a name for it and a shorthand notation is because it comes up all the time in the real world. There's lots of applications for it. There's something called, your book calls the slice and sum method. And this is something you do a lot in physics. You also do it in economics and, well, lots of things. But the slice and sum method is anytime you're trying to calculate something that changes and you don't know how to calculate it, you split it up into little tiny pieces and you add them all up. Then you take the limit. And when you do that, you're ending up with an integral. So that's a definite integral. Now the thing about a definite integral is that this limit, I mean, this is a really strange limit. And there's no reason to think it's always defined, right? You talked about in the past about some limits not being defined. So we call this a function integrable if you can actually take this limit, if it exists. And no matter how you choose the rectangles, so if you do right, you do left, you do midpoint, you do completely random stuff, you always get the same answer, right? Because that's what would make sense. You should always get the area under the curve. You should always get the same thing. Although there are some really weird functions out there that if you can come up with if you try really hard where this isn't actually true. All the ones we're going to deal with are going to be integrable. But you should remember which ones are going to be integrable. So if your function is continuous, or if it only is discontinuous in a finite number of places and it jumps around, so we're talking piecewise functions here, right? If it does this, then it's still integrable. But if it's got asymptotes, if it's got weird behaviors, then it may not be integrable. Okay, so what's cool about things being integrable? Well, what's so cool about it is if they're integrable, that means that you can take the rectangles however you want. Well, okay, sure. But that means I can pick the rectangles in the easiest way possible, and I'm still going to get the right answer. So I can always take all my widths to be the same. So forget this, different rectangles have different widths. We can always take delta x being b minus a over n. And we can always take the heights the same way. So when we take the heights, the easiest one, remember, was the right endpoint. So usually that's the one we're going to do, but we'll also do a few where we do left or midpoint. So that means that sum, or that integral, the definite integral, you could just write that as the limit as n goes to infinity of the sum, k goes from 1 to n, of f of a plus k delta x. Remember, that's the grid point for rectangle k, times delta x, where delta x is b minus a over n. So that's the formula. That's the main formula you're going to be using. And if we look at this interactive figure here, you can see that here they're actually doing left midpoints, but if you do left, it gets really close. You could also do left endpoints. You could also do midpoints, and using midpoints, it also gets really close. Or you can do right, and using right, all of these ways, once you take the limit, you're going to get the same answer. And so here's the formulas for the right, left, and the midpoint. We already did all of this without the limits in front before, so the only things new is that we're just adding the word limit there to get the exact area. There's a kind of different concept here, though, because once you put the limit in, all of these are going to give you the same answer. But without the limit, they give you different answers. Okay, so what properties does the definite integral have? What can we do with it? Well, the first thing to be careful of is I keep saying area under the curve, but that's not exactly true. We're actually finding what's called the net area. And the net area means that any area where the graph is actually above the x-axis, we're finding the area under the curve. Right? And so as long as your function is positive, you're fine. But if you're below the x-axis, you're finding the area below the curve. But what's more, you're going to get a negative number for that. Because think about how we're finding height. We're finding height by the f value, the function value. And so here, the f value is negative. So when you multiply the negative number by the positive width, you actually get a negative contribution to your sum. So instead of telling you, you'd think maybe that if, let's say, pretend this one's 5 and this one's 7 and this one's 3. So you'd think if you're talking about the area under a curve, you might add up all those numbers. But that's not actually true. What you do is you add up the two positive contributions, and then you subtract off the negative contribution. And that's how much the Riemann sum is going to be, the definite integral. That's what the definite integral is going to give you. Right. So another property of the definite integral is if you switch the limits, if instead of going from a to b, you go from b to a, then that's going to make your answer negative. And the reason for that is normally delta x is b minus a over n, right? But if you switch the places of the b and the a, delta x becomes a minus b over n, which is the same as b minus a over n, except there's a negative sign out front. So that negative sign is going to come in right where this delta x is, and you can pull it right out front. Now what if you're taking the area between a and a? So we got, we're starting here, and we're ending right here. We have an area that's infinitely skinny. It's got a width of 0. What should you get? Well, you should just get 0. If you take a height times a width, and the width is 0. All right, what about if you're taking the integral of a constant function? Well, the constant function, remember when you graph it, it's just a horizontal line. So if you're finding the area under it, it's just a rectangle. How do you find the area of a rectangle? You do length times width. Well, the length in this case is b minus a, so this distance here. And the height is just your function value, c. So you get b minus a times c to be the answer to your integral. If you take the integral of a constant times a function, you can pull the constant out front. That's because if there was a constant times your function in the sum, you could pull it out front. And if you have an integral of two functions that are added or subtracted, you can split them apart into two separate integrals. And that's because you can do that with the sums, right? The sum of a plus b is sum of a plus sum of b. Okay. Now this one's a little bit weird. This one says if you're integrating two regions that touch at C, then you might as well just integrate it as one big region. So let's look at the pictures here. So say you have this integral that's going from A to C. And C can be any number here between A and B. And then you have another integral. So you're going from A to C. So you're taking this light blue area. And then you have another integral that goes from C to B. So you're taking the dark blue area. Well, if you take those two areas and add them up, you're going to get the same area as if you started at A and just went all the way to B. So that's what this says. Now what about if the C is on the outside? Because that one kind of bothers people. If the C is on the outside of the function, it still actually works, but you end up subtracting. Because you say that if you were going from A to C, then you get the whole thing. But remember that from B to C, but if you subtract off what you get from B to C, then you would just get the A to B part. So notice that this formula is slightly different because it has a minus sign, and it has from B to C. And the other formula had a plus sign, and it had from C to B. So are those two exactly the same formula? Actually, they are, remember? Because if you switch the orders of the limits of integration, you have to switch the sign out front. So this is just the same way, way of saying the exact same formula. All right, so what else? If you have a function that's always positive, then your integral has to be positive. Well, that makes sense, right? Because you're taking a positive area. If you have a function that's always bigger and positive, or is always bigger than another function, then its integral is going to be bigger because look, this area for the f of x contains the area for the g of x. So it's got to be a bigger area. And if you know a number that's always bigger than your function, then the area of that box has got to be more than the area under the curve. And if you know a number that's always littler than your function, then the area made by that box always has to be less than your area under your curve. Because the area under your curve is contained in the big box and contains the little box. So this doesn't seem like it's all that useful, except sometimes it really can be. Because sometimes it's hard to actually find the exact area, but you can estimate it pretty well by saying it's trapped between its biggest value box and its smallest value box. So those are all the properties of definite integrals. So let's try using some of them. Is there ways that we can actually evaluate definite integrals without having to, do complete Riemann sums every time? Sometimes there is. So here we've got a graph g of x. It's got two straight lines and a semicircle. And we're supposed to evaluate each of these integrals. So a is the integral from 0 to 2 of g of x dx. So from 0 to 2, the curve looks like this. So the area we're finding is actually the area of this triangle. So we could figure out the equation of that line, and we could make a summation out of it, and we could take a limit. But that sounds like a lot of work. We know we're trying to find the area, so let's just use the area formula for a triangle. 1/2 base times height. So 1/2, the base here is 2, and the height is 4. So we just get 4. That was easy, right? This is called using geometry to solve integrals. So question B says the integral from 2 to 6 of g of x dx. So the integral from 2 to 6, now here this is negative, and we're trying to find the area of a semicircle. So it's going to be the area formula for a semicircle, which is 1/2 pi r squared. Pi r squared is the area for a circle, a half, because it's only half a circle. But we have to put a negative sign in because it's below the x-axis. And so in this case, it's negative 1/2 pi, and the radius is 2. So we end up with negative 2 pi. All right, and then C, this is the interesting one, is the integral from 0 to 7 of g of x dx. Now that's this whole thing. So we're going to take the positive of the two blue triangles and the negative of the circle. And the way we're going to do that is we're going to think of this integral in 3 pieces. We're going to think of it as the integral from 0 to 2 plus the integral from 2 to 6 plus the integral from 6 to 7. Now that's just that thing where you can split it up at points in the middle, that ABC stuff we were talking about. So we know the integral from 0 to 2, that's 4. We know the integral from 2 to 6, that's negative 2 pi. And to find the integral from 6 to 7, well, that's just this little, 1/2 times the height, which is 1, times the base, which is 1. So it's just a half. So the integral from 0 to 7 of g of x, the net area under the curve between 0 and 7 is 4 minus 2 pi plus a half. All right, our next example says write the Riemann sum as a definite integral on the interval from 3 to 8. So we have a Riemann sum here. And they want us to say, if we take the limit of this Riemann sum, what integral would it be? So this is an interesting kind of problem. What we want to do is try to match it up with the general form of a Riemann sum. So here is a right Riemann sum. Now notice this problem uses i's instead of k's, but that doesn't make any difference. All right, so what can you see that kind of matches up? Well, the 5 over n at the end looks like a good candidate for delta x, right? Because delta x is supposed to be always b minus a over n. So it should be some number divided by n. So if it were 5 over n, that would tell you that b minus a is 5. And then we can also match up 3 plus 5i over n. There's 2 of those. But either one of those matches up with the a plus I times delta x. Because that is that's supposed to be our x bar, xi bar. So if those match up, that would mean it looks like maybe 3 is a, which is supposed to be, 3 is supposed to be a, and b is supposed to be 8. So 3 and a match up. And then the i's here match up, and the delta x matches up with 5 over n, which is what we already said it should be. So that looks good, right? So we can first simplify this sum into saying that it's the sum I goes from 1 to n of sine of xi bar over xi bar times delta x. But now it's pretty easy to turn that into an integral, because the integral matches up with the sum sign. You always say going from a to b, so going from 3 to 8. What's the function? Well, the function is sine of, instead of xi bar, we just say x divided by x. We replace all the xi bars with just plain x. And then the delta x becomes the dx. So this is how you write it in integral notation. Okay, now this one, we're going to use properties of integrals to solve a problem when we don't actually know what the function even is. So it tells us that if you integrate from 0 to 10, you get 17. And if you integrate from 0 to 8, you get 17. So what do you get if you integrate from 8 to 10? Well, the integral from 8 to 10 is going to be the integral from 0 to 10 minus the integral from 0 to 8, right? Because we want the area just between 8 and 10. So we'll take the whole area from 0 to 10 and get rid of the area just between 0 and 8. Well, that's 17 minus 17, so the answer we're looking for is just 0. All right, so now here's a problem we're actually supposed to calculate out an integral using Riemann sums. So we're using the definition of the definite integral. That's what it's called. Let me write that down. Definition of the definite integral. So if you see those directions, then you're supposed to do this. You're supposed to say this is the limit as n goes to infinity of the sum, k goes from 1 to n, f of a plus I, k delta x times delta x. Okay, so then that means it's the limit as n goes to infinity of the sum, k goes from 1 to n, of, well, what do we know about this? Let's write down its properties. We know that 0 is going to be a. We know 5 is going to be b. That tells us that delta x is going to be b minus a over n, so it's going to be 5 minus 0 over n, or 5 over n. Our function is what's right here. That's our f of x. And that should give us all the information we need. So we're going to have f of a plus k delta x. So a is 0. K is just k. Delta x is 5 over n. And then outside here, delta x is 5 over n. All right, so then we have limit as n goes to infinity, sum k goes from 1 to n, and we're going to have to use our function. So our function is 1 plus 2 times the quantity of our x value cubed. And then that whole thing is going to be multiplied by our delta x, which is 5 over n. So what is the quantity of our x value? What's our x k bar? It, in this case, is 5k over n. So now we need to simplify this limit. Remember, using sigma notation rules. Now the sigma notation says I can pull out constants, so that's pretty easy. I see a constant right away. I can pull out this 5 over n, so I'll start there. 5 over n, limit is, whoops, not outside of the limit though. Limit as n goes to infinity, 5 over n, sum, k goes from 1 to n, of 1 plus 2 times 5k over n, that's 5, cubed. Okay, so now I can use the rule that says I can split things over sums to make this into two different sums. So I'm going to have limit as n goes to infinity of 5 over n. Now the 5 over n applies to everything, so I need some big brackets. Sum k goes from 1 to n of 1 plus sum k goes from 1 to n of 2 times, we can just say this is 5 over n cubed times k cubed. Now, the sum k goes from 1 to n of 1, I'm done with that one, right? I know the formula for that. The formula for that is just n. But to finish off this second sum, I need to pull out all the constants. So I'm going to pull out the 2 and the 5 over n cubed, and sum it, k goes from 1 to n of k cubed. And now, this one matches up with the formula the same way this one did before. So I have limit as n goes to infinity of 5 over n, sum n plus 2 times 5 over n cubed times, the cubed formula is n times n plus 1 over 2, the whole quantity squared. And now I'm down to actually just doing a limit. Now the first thing I want to do when I have one of these more complicated limits is I want to distribute out this 5 over n, or whatever my delta x is, distribute it out to every term. So I'm looking at limit as n goes to infinity, 5 over n times n, which is just 5, plus 5 over n times 2 times 5 cubed over n cubed times n squared times n plus 1 squared over 2 squared. All right, so I'm taking the limit of that whole thing. The first limit is pretty easy. The limit of a constant is just 5, it's just that constant. Now the second one, I want to use that shortcut theorem. So what's going to be the biggest power of n on top? If I were to multiply everything together, I would have a 5 times 2 times 5 cubed times n squared from this term, times if I fold this out, the biggest thing would also be an n squared. And then on the bottom, I have n times n cubed times 2 squared. So multiplying that all together, I get 5 plus limit as n goes to infinity of 5 to the 4th times 2 times n to the 4th over 4 times n to the 4th. Canceling the n to the 4th, I get 5 from before plus 5 to the 4th times 2 over 4. And that's my area. Once you've taken the limit, you're done. All right, one last thing to talk about in this lecture, and that's one of these applications that is the slice and slice up method. And that is if you're given velocity and you're trying to find distance. So suppose we had a car that's traveling for 2 hours, and its velocity during that time is given as this formula, 30t plus 10. And we're asked how many miles has the car traveled. All right, so the car, it's traveling in a straight line, so that's nice, but its speed is changing. So first of all, if I gave you an easier problem, one where the speed's not changing, if the velocity was always, say, 30, and you go for 2 hours, then what would your distance be? Well, it'd just be 30 times 2. You're going 30 miles an hour for 2 hours, so you'd have gone 60 miles, right? You just multiply the velocity and the time. Okay, but this one is a little bit different because the velocity is changing. So how do we do it? We're going to use the slice and sum method. What we do is we slice it up. So let's say we are going to approximate by pretending it's going at constant speed for 20-minute intervals. So like the first time we'll measure it at is after 20 minutes, which we're in hours, right? So 20 minutes is really a third of an hour. So after 1/3, the velocity is going to be 30 times 1/3 plus 10, which is 20. After 2/3, it's going to be 30 times 2/3, so 60 plus 10, so 70. And then after an hour, it's going to be, no, not 70. That's not right. Okay, 2/3, it's going to be 30 times 2/3 plus 10, or 30. After an hour, it's going to be 1 times 30 plus 10, so 40. After 4/3 of an hour, it's going to be 50. 5/3 of an hour is going to give you 60. And after 2 hours, you're going to be going 70 miles an hour. All right, so we can approximate the speed by saying for the first 1/3 of an hour, we were going about 20. Plus for the second 1/3 of an hour, so the length of time for the second interval was 1/3, we're going about 30. And for the third 1/3 of an hour, we're going about 40. Plus for the next one, next 1/3 of an hour, we're going about 50. Plus the next one, we're going about 60. Plus the next one, we're going about 70, right? And if we added all those up, that would give us an approximation of how far we've gone. So let's look at this kind of as a picture. If this is our graph of our velocity function, then we've said that over the first 1/3 of an hour, we're essentially going 20 times the 1/3, or the area of this rectangle. Then for the next 1/3 of an hour, we're essentially going 30 times the 1/3, so the area of this rectangle. 40 times 1/3 gives us this rectangle, and so on and so forth. So what have we done? We've split the velocity function, the area of it, under it, into rectangles and added them all up. We've done a Riemann sum. We just didn't realize it, or maybe you did. So if we wanted to be more accurate, what would we do? Well, we would take our velocity measurements more often, right? Instead of every 20 minutes, maybe we would do it, instead of 6 times in those 2 hours, maybe we'd do it 14 times, or maybe we would do it 51 times, or maybe we would do it 151 times, or 200 times. So how are we going to get the exact distance that we traveled? Well, the exact distance is going to be the limit, right? It's going to be the limit of the sum of all the rectangles, I goes from 1 to n, but it then goes to infinity, of the velocity at each time times the width of the time interval. Does that make sense? So it's just a Riemann sum. So in this particular case, it's going to turn into the integral from 0 to 2, because we're going over the time period from 0 to 2, of 30t plus 10, because I should say delta t here, because we're using t as our variable. 30t plus 10 dt. And that is going to give you the distance traveled. So what does that tell us? That tells us that if you want to go from velocity to distance, you can just take a definite integral. But we also know something else about distance and velocity. What if you want to go from distance to velocity? What do you do? you take a derivative, right? The derivative is the rate of change. It's the speed that something's happening at. So this is kind of interesting. It leads us to wonder, to make the hypothesis, maybe there's a relationship between derivatives and integrals. In fact, maybe we can be a little more specific. It seems like that taking an integral seems to undo the derivative process. So that's let's make that our hypothesis, that integrals undo derivatives in some way. Okay? And we're going to go, this is going to be the topic of our next lecture. So this is just kind of a preview. This is where we're going with this. This is why they're both considered calculus, because they're all tied together here. Before we talk about that, I want to give you one caution about this distance and velocity stuff. So I was asking you about distance traveled, how far that car went, right? In general, the definite integral only gives you displacement. It doesn't actually give you distance traveled. Let me show you what I mean by that. So let's look at this figure here. So in this setup, say we're given this velocity function right here, and we're asked to find the distance that this dot travels if it's going using this velocity function. So that would be, if we use the definite integral, it'd be the area of this triangle minus the area of this triangle. So let's set this in motion and see what happens. So if we hit start here, as the velocity is positive, the dot is moving forward. Once the dot velocity becomes negative, the dot's moving backwards. So what happened to the dot? It moved, but the displacement is 0. That means that how far is it from where it started? So distance from starting point. And that's what you're going to get if you take the definite integral, because this top triangle and this bottom negative triangle are exactly the same area. So adding them up, well, subtracting them really, but putting them together, you're going to get 0. And that makes sense because the dot is actually in the exact same place it was before you started. Now, if somebody asks you about distance traveled, that's different, because the dot didn't just stay still, right? It went all the way up here, and then it came back again. So it traveled a long distance. Well, how would you find the distance traveled? You would have to take the positive value of this triangle plus the positive value of this triangle. That would give you the distance traveled. But in this case, if you want the positive value of a negative number, you want the absolute value of it, you would actually subtract it. So you'd be looking at the integral from 0 to 2 of the velocity function minus, because you want the absolute value, you want the positive, and this integral will give you a negative, the integral from 2 to 4. So that's just a caution. You remember, this is kind of like net area. Displacement is the same as net area. It corresponds to net area, versus distance traveled corresponds to actual area. If you consider both the positives, the above the x-axis and below the x-axis as positive. All right, so that concludes our lecture for today. Thank you very much.